Algebra Crew. This is your Chapter 9, Lesson 1 video, but before we get into it, I want to just go through what Chapter 9 is going to look like. So in Chapter 9, we're going to talk about radical expressions. So this is square roots. It turns out that any number can be under a square root, but it's got different meanings depending on what that value is. And so we're going to talk today about what the square root really means, what the number under it really means, and then how to what we call simplify a radical. Then we're going to talk about simplest form of radicals in a little bit more of a higher level setting, and that will be useful for us in chapter 10. And then we're going to determine rationality. And so we'll review what makes a number a rational number versus an irrational number, and how to determine the rationality of a number, especially given a word problem type of circumstance. Okay? Very short chapter. We'll be done with it in a week. You can see 1, 2, 3, 4, 5, 6 days, right? Okay. So let me start with simplifying radicals. And this is day 1 of the notes because this is so new for you. First of all, a radical is what we call the square root sign. Okay, so the square root symbol actually has lots of other ways it can be interpreted depending on what we're trying to take the root of. Okay, a square root symbol is me trying to ask you what number times itself had given me this number under the square root, called a radicand, the number under the square root. Okay. When I put 25 under the radical, I am asking you to tell me what is the number that times itself, the product of this number with itself, gave me this value right here. Okay, the radicand value. So when I take a square root of something, I am looking for that value that comes from a product of a number times itself. Now, typically, we only deal with the principal root, which is when you take the square root of 25, you say 5. Well, actually, it's 5 and negative 5. But we mostly refer to the principal root, the positive root coming out of a radical, unless we are told otherwise. And that will be something that we address in this chapter, chapter 9, and in chapter 10. Okay? But to address it quickly, 8 squared is 64, and negative 8 squared is 64, which means that if I ask you the square root of 64, technically the answer to this is plus and minus 8. But if you only give me positive 8, you are giving me the principal root. You can already see where I'm going with this next part. You got to know what your perfect squares are, because you need to be able to identify a perfect square if it's under the radical, or if it's a factor of your radicand. That's where we're really heading, which means you really need to know your perfect squares. You've just got to know your perfect squares. And the awesome part about perfect squares is that variables can be perfect squares too. Because when you take x and multiply it by itself, you have just squared x, which means that x squared is a perfect square. We learned that already, and we've used that in chapter 7 and in chapter 8 for dots, difference of two squares. And we knew we needed to memorize our perfect squares then, because there are so few of them as far as the amount of numbers go, that really, if we memorize these first few perfect squares, we've got a lot of our perfect squares, right? The ones that we will see quite frequently. There are only so many perfect squares. In fact, for the first 400 integers, there's only 20 perfect squares. Only 20 of the first 400 integers are perfect squares. And you can see them listed here. Okay? So perfect squares are like 1, 4, 9, 16, 25, 36, 49, 64, 81, 100. Because if I put these values under a radical, the square root of 1 is plus and minus 1. The square root of 4 is plus and minus 2. The square root of 9, plus and minus 3. So you can see what perfect squares mean. So here it's more in your face exactly what these things mean. Okay? Perfect squares are the products of a number times itself. So when I take the square root of a perfect square, I get that original number back out. That number that had been multiplied by itself. Now, because out of the first 400 integers, only 20 of them are perfect squares, means the majority of the numbers that are under a radical sign aren't perfect squares, which means you cannot take their square roots, which means there will be a number left under the radical, which means it's irrational. So this all goes back to chapter 1, lesson 1. Any number under the radical that's not a perfect square is irrational. It's a non-repeating, non-terminating decimal. And so as a result of that, we need to know how to deal with those things. Well, it turns out that a perfect square can't be left under a radical, even if it's just a factor of the number that's under the radical. We always have to take perfect squares if they're under the radical. We can't leave them be. So that's the procedure that we're going to practice today and tomorrow, called simplifying radical expressions. We're going to take radicals like radical 24, and we are going to simplify it, meaning if there's a factor in 24 that's a perfect square, we need to take it out as taking its square root, and then that becomes the coefficient in front of it, and the leftover piece that's not a perfect square stays under the radical. Okay, so let me walk you through simplifying the square root of 24 first, then I'll throw out another example, and then we'll do more practices together, and then practice the homework so that we can be ready for more practice tomorrow. Because really the best way to do this is to A, have your perfect squares memorized, and B, practice simplifying, because you're just going to have to be able to do it. This doesn't go anywhere either. A lot of the stuff we do, everything we do, doesn't go anywhere. It keeps being used in geometry and algebra 2 and any other math that you are taking from this point forward. So if I have radical 24, the first thing I ask myself about the number under the radical is this a perfect square? If the answer is no, the next question I ask myself is, well, is the radicand evenly divisible by a perfect square? And so I think, well, everything's divisible by 1, so that's not the perfect square that counts. I start with 4. Is 24 evenly divisible by 4? Oh, yeah. In fact, 24 results from 4 times 6. So since 4 is a perfect square and 6 is not, I'm going to call it the leftover, LO for leftover. Since 4 is a perfect square, I put it under its own radical so that I can take the square root of 4. Notice only my principal root is coming out. But this 6, it's in this radical, and I can't take its square root. This is the one that stays. And now what you do is, since these two pieces are factored pieces, they're multiplied together, you now combine them back together without the dot between them, calling this 2 radical 6. Say it with me so you know how to say this number. 2 radical 6. 2 radical 6. This radical is simplified. That's your simplified answer. It is, of course, irrational because there is still a number under the radical that cannot come out. So this is an irrational number. Okay? Now, if I had this, radical 25, Remember, the first question I ask myself is this a perfect square? Here, the answer is yes. I would just take it, again, principal root. So positive 5. Notice this is rational because there is not a perfect square. Excuse me. There is not a radical left over. Radical's gone. It did what it was supposed to do. It asked you to find what was the number times itself that gives me 25, and you did. There is not a number times itself that gives me 24. So I did the next best thing, which is find a factor in there that could. And I took its square root. That was the closest thing I could get. Okay, let me show you another one. Very close to these ones. Radical 28. So that radicand is close to the two I've been working with, right? Is 28 a perfect square? No. Is 28 evenly divisible by any perfect squares? 4. Oh, yes. What is the result of 28 divided by 4? 7. So what I do is I divide my radical into a perfect square radical and a leftover radical. Now these radicals are multiplying together, so I could write this dot in there. I don't tend to, okay? I don't have to. But these are two radicals that are multiplying together. Well, in this one, I can take its square root, and this one is left over. So my answer is 2 radical 7. Say it with me, 2 radical 7. Nice job. Let me show you another one before I really get into the rest of them, right? I'll even go down one. 27. I'm being asked, what's the square root of 27? 27 is not a perfect square. Okay, so since 27 is not a perfect square, let's think if it's evenly divisible by any perfect squares. Start with 4. 27 is not evenly divisible by 4. Okay, so get this and prove. Darn it. So now let's try the next perfect square, which is 9. Is 27 evenly divisible by 9? Yes. And look at that leftover. No perfect squares divide evenly into 3. So now what you do is divide 27 into 2 radicals, the perfect square radical and the leftover radical. So this radical 27 has now factored into 2 radical pieces. You take the square root of the perfect square radical, bring that up front, and you leave behind the radical leftover at the end. 3 radical 3. Say it. Nice practice. Practice saying your answers as well, and I will continue doing so. Okay? What I'll do as I do these practices over here is I'll divide these into perfect square and leftover. So I'll do a couple, then I'll leave you to do a couple. Okay? I'll do, how about I do the odds? You guys do the evens. Okay? So radical 45. Okay. 45 is not a perfect square, but it is evenly divisible by a perfect square. So it's not 4, and then I try 9, 9. So I divide radical 45 into 2 radicals, a perfect square radical and a leftover radical. What's the square root? Excuse me. What perfect square divides evenly into 45? 9. That goes under the perfect square. Now 45 divided by 9 is 5. That goes under the leftover. Now you take the square root of the perfect square, which is 3, and you leave the leftover, which attaches by multiplication for the end result. 3 radical 5. Say it. Nice job. Okay, I'm going to do 108, and I stopped. I hesitated for a second because there's a lot of perfect squares that actually divide evenly into 108. It itself is not a perfect square, but I just want to show you something. I'm going to take 108 and I'm going to start dividing it by perfect squares. Ready? I start with 4. Oh, hey, that works. I could go with 4 if I wanted to. The problem is the leftover. If the leftover can still divide by a perfect square, you have not found the biggest perfect square that divides evenly into your radicand. So let's keep going. Let's try 9. 108 divided by 9. Okay, that evenly works. But again, 12 divides by a perfect square. So I'm not finding the biggest perfect square yet. Okay, well, let's try the next one, which is 16. So 108 divided by 16 does not give me an integer for a leftover. So let's keep going. My next one is 25. Okay, does not give me an integer for a leftover. So let's keep going. 36 is the next one. We're starting to get high numbers, but you keep trying until you get a leftover that also is not evenly divisible by a perfect square. So radical 108 divides into radical 36, which is our perfect square, and the leftover. 108 divided by 36 is 3. So now I take the square root of the perfect square radical. I get 6. That's now my coefficient. The radical 3 is now attached by multiplication at the end. And our answer is 6 radical 3. That's it. Nice job. Again, 50 is not itself a perfect square, but it is evenly divisible by a perfect square. Not 4, not 9, not 16. 25. Notice I'm only trying perfect square factors. So there's a specific list of factors to go down. 4, 9, 16, 25, 36, 49. There's a specific list. I don't have to try a lot of numbers because I have my perfect squares memorized. I know exactly which numbers to try. It's got to be a perfect square, right? So radical 50 divides into perfect square radical of 25, and a leftover radical of 50 divided by 25 is 2. Take the square root of 25, which is 5. Radical 2 is the leftover, and 5 radical 2 is my final answer. That's it. 5 radical 2. Good job. 68. Ooh. Well, let's try 4. I'm thinking 4 because, well, of course, I have to try 4 first anyway. Oh, well, look at that. 68 is evenly divisible by 4. My leftover is kind of a high value, 17. But 17's prime. That's it. That's my leftover. Not divisible by a perfect square. So I divide radical 68 into perfect square and leftover radical. Perfect square is 4. The leftover is 17. Take the square root of 4, you get 2. Bring the leftover radical along, and you've got 2 radical 17. Go ahead, say it. The last one I'm going to try before we pause it and let you try the evens is a radical that already has a coefficient. So it's like someone kind of tried to start simplifying it and didn't finish, because this radical 27 still has a perfect square factor. So what you do this time is you just bring that coefficient with you. So negative 2 just comes in front of my perfect square and leftover radicals. Okay, so now radical 27, it's evenly divisible by 9 is my perfect square that goes into 27. 27 divided by 9 is 3. Okay, now I take my square root of 9 and I get 3. Well, there was already this coefficient of negative 2. So multiply negative 2 times 3 to get your final coefficient, which is negative 6, and bring that radical 3 along, multiplied together for the final answer. So say it with me, negative 6 radical 3. Excellent. When you see one of these numbers, that's how you have to read it and say it, okay? So 3 radical 5, 6 radical 3, 5 radical 2, 2 radical 17, negative 6 radical 3. Those are the answers I've gotten so far. Pause right here. We're going to come back and show you the final answers for the evens, but pause right here and try these. And I'll be right back with answers for you. Good luck. Okay, algebras. Let's stop here, check our answers. I'm going to read them. I want you to say them as well. So practice saying what these answers are. 2 radical 6. 3 radical 2. negative 2 radical 7, 7 radical 2, 10 radical 14. Make sure you're memorizing your perfect squares. Make sure you're using your perfect squares to test for factors of your radicand. Make sure your leftover cannot divide evenly by a perfect square. So I know in the case of number 10, it's weird to think of 14 as a leftover because it's an even number. We think, oh, it's divisible by 2. 2 is not a perfect square. So things like that are going to stay under a radical. That's it. They're not divisible by a perfect square. They're not going to be able to come out of a radical. All of these answers are irrational, okay? Meaning the radical is still involved, not a perfect square under it. It's got to stay, okay? These would be non-repeating, non-terminating decimals if I plugged them into my graphing calculator to try and see a rational equivalent, okay? So just a heads up, we're going to do this again tomorrow because this is on the newer side and it can be tough. I'll probably barrel through a little bit faster tomorrow, knowing that you have your perfect squares memorized from chapter 7 and chapter 8. Oh, and way back in chapter 1 when I first mentioned it, right? Right. Okay, guys, this has been your chapter 9, lesson 1, day 1 notes. Good luck on your homework tonight. Ask me any questions if you have them. I am more than happy to help you. I'll see you for day 2. Bye, guys.